Welcome everyone to today's GOCC. Before I introduce the speaker, let me recall our community statement, which has 3 guiding principles. The first one, we are all learning. The second one, everyone has something to contribute. And the third one, no one has all the answers. With that said, I want to hand over to Eva Maria Heinzel from TU Wien, who will talk about geometric dominating sets. Eva, please take it away.
Thank you, Stefan. This is so nice that you're having me. Before I go straight into the material, geometric dominating sets, let me do like a small informal introduction. So if you know dominating sets or geometric dominating sets from graph theory or something, then I'm sorry to disappoint you. This has nothing to do with it. It's something new. The research on this problem was initiated in 2018 at the workshop on computational geometry on Barbados, where my co-authors Oswin Eichholzer and David Epstein met. And they initially started to talk about with other people about point sets in general position. I will explain later what point sets in general position are. But the long story short, Oswin Eichholzer became my master thesis advisor and presented me with this problem. And this is eventually what we got out of it. And we recently submitted like a full paper. So we introduced the problem at a conference in June, and we recently submitted. And I will maybe next week or maybe even this week put the preprint on the archive. So if you're interested, maybe look out for it. Okay, so what are geometric dominating sets? We take an n times n integer grid, and we take a subset of this integer grid and call it a geometric dominating set if every point in the grid is in the set, or it lies on a common line with at least 2 points from the set. So I'll show you a picture. We have this n times n grid, or I don't know, some of you are doing algebraic combinatorics, so maybe you prefer the word lattice or something. So what we're talking about are these intersection points of the lines, essentially, an n times n integer grid. And then this would be, for example, a trivial dominating set, which would just take all the points in the set. Every point is in the set, so it's a dominating set. We could also just take 2 columns in the set, well, then every point in the 2 columns here are in the set, are dominated, and every point in the middle is dominated, for example, by a horizontal line that is spanned by these 2 points. The points on this diagonal are also dominated by a line from this point and this point. There's also lines like with different slope, like we could also consider lines with slope 1/2 here. I mean, this doesn't work out on an 8 times 8 board, but theoretically, if you would place a point here, these are also feasible lines in the n times n integer grid. So maybe let's look at the dominating set that is a bit more interesting, maybe like this one. It only has 12 points compared to the 16 points that we had before. And it's not so obvious anymore that it's a dominating set, but well, just the points in the edge, in the corners dominate the outer edges essentially, and the diagonals, and the rest of the points are dominated, for example, by these lines. So we went from 64 points to 16 points, now 12 points. Very natural question is, what is the smallest? And well, this dominating set, for example, does not contain collinear triples. So every point in the dominating set is only dominated by itself, right? This is like an extra property of the dominating set that can be interesting. And then the question is, what is the smallest set of a dominating set without collinear triples? And just to give these notions like a variable, we say that the smallest size of a geometric dominating set of the n times n integer grid is called geometric domination number, and denoted by dn. And in case that we do not allow collinear triples in the dominating set, we call it independent domination number, and we denote it by in. Yeah. So maybe as a solution to our 8 times 8 board that we considered before, in this case, D8 and I8 coincide. This is usually not the case, but here they coincide, and it's 8. And these are, for example, 3 sample optimal sets, optimal dominating sets. And they're all without collinear triples. And you can see, well, this one is, for example, very symmetric, the left one. The right one, there's no symmetries at all. So at this point, we have computational results up to n is 12, I think, some larger numbers, but not optimal sets, or not necessarily optimal sets. And there's no real pattern or something of that kind. I'll quickly tell you what we know about dominating sets in the n times n grid in the plane. But where I actually want to get us is the discrete torus, because this was my favorite part, and it's also a bit more fun in my opinion. But in the plane, we know that the domination number is bounded asymptotically from below by n to the 2/3. This is based on a counting argument, essentially. And it's bounded from above by n if n is even, and n plus 1 if n is odd. The upper bound is based on a construction, but we also know that it's not tight for n larger than 8. I mean, at least for small numbers, we know it's not tight, and we assume as n gets large, it will definitely not be tight. So yeah, we think this number should actually be strictly smaller than n for n large. For the independent domination number, we just know the lower bound, because any dominating set without collinear triples is just a dominating set. So In is bounded by Dn. And so the lower bound for Dn also holds for In. And for an upper bound, we have no non-trivial upper bound. We just have as an upper bound 2n. That is obvious if you think about the n times n grid has n columns. If we would have more than 2n points, we would have a column with 3 points. So we would have a collinear triple, which is impossible by definition. However, there's a conjecture on a very connected problem. It's called the no-3 line problem, and this is an open problem. It's been an open problem for more than 100 years now. So if you're looking for a real challenge, this is maybe the thing that you're looking for. The no-3 line problem asks for the maximum number of points that can be placed in the n times n grid, so that no 3 points are collinear. And there's a conjecture from 1968 from Richard Guy and Patrick Kelly. And they conjectured that for large n, we expect to be able to select approximately some constant that is smaller than n times n points, smaller than 2 times n points with no 3 in line, but no larger number. And only in 2004, Gabor Ellman found like a computational mistake and corrected this constant that they initially published to pi over square root 3, which is definitely smaller than 2. We will later talk about this conjecture. I will get back to it. It's based on heuristic arguments, and we will sort of extend that thought, that idea. But like I said, I actually want us to get to the discrete torus. So maybe I first introduce the discrete torus now. What's a torus? A torus is just this donut shape in 3-dimensional space. So if you do not know what a torus is, just think of a donut. And if you want the discrete torus, just think about like computer graphics. You put a mesh on it, and then you just consider, again, the intersection. This is the discrete torus. And then a sample line on the discrete torus, well, it would like wrap around the torus like this. And we only consider the points in the grid, right? So this would be, as the magenta points would be a sample line on the discrete torus. And mathematically, it's very easier to think about the if you just cut it open here. So you cut it open such that you only have a pipe. And then you cut the pipe again, maybe along this line or something, and you fold it open, and you basically just have a sheet of paper anymore. And then you end up essentially with this gray area here. You have an n times n grid. And you can undo this operation if you to this edge, then you have the pipe. And then you glue this edge to this edge, and you're back again at the donut, right? And then the sample line that we had that wrapped around the torus, it's actually just a line in the plane, in this integer grid in the plane. And the points we take modulo n. So here modulo n, we end up here. And then this point modulo n, we end up here. This point modulo n, we end up here. This point modulo n, we end up here, and so on. And we get out of here, and then modulo n, we are again here, and so on, right? Maybe I should also point out there's a couple of lines in the plane that project onto the same line on the torus. Like this line is in the plane is a distinct line from this line, but on the torus it's the same, right? So in formal terms, the discrete torus is just the integers from 0 to n-1 times this integers from 0 to n-1. And lines on the torus are just images of lines in the integer grid in the plane under the projection modulo n. And when I say modulo n, I really mean just the smallest non-negative remainder when we divide x1 by n, not the congruence class, just something that you might remember from algebra or something. This is just a simple integer.
I had a quick question. Could you go to the previous slide?
Yes.
So I think this doesn't, it looks like we're off by one, like my rectangle, my square should be like one square larger to me. Because like, shouldn't that point, if I've got a point in the bottom left-hand corner, because I'm identifying my side, shouldn't it kind of be in every corner of my square?
So, okay, this is maybe a bit confusing, but this point is congruent, the same point.
Right.
Those 2 points are congruent, right?
Okay.
Does this answer the question, or did I?
Yeah, so I guess it just felt like the gray stopped.
Yes. So maybe it would have been better to like extend the gray area to the middle of this thing.
Yeah, that intuition's on track. Carry on.
Okay. Perfect. No, very good that you're asking these questions, because there's no point in doing this talk if I lose you already in the beginning. Right. So this was the intuitive thing. This was the formal thing. And now maybe let's make some observations about lines on this torus. Let's take the 11 times 11 torus, and we take the point 0, 0 and 4, 4. And then they span a line, of course, this diagonal line. And now, because 11 is a prime number, 4 has a unique inverse. So there's really only this one line that is defined by these 2 points. If we would be on a 10 times 10 torus, and we would still consider 0, 0, 4, 4, then we also have this diagonal line. But we would also have, like, for example, this green line here. Because if we go down 2, 3 right, 2 down, 2 down, 3 right, modulo n, we're here. And we go down 2, 3 right, 2, 3 right, 2, 3, 2, we end up here, 2, 3, 2, 3, and we're back. This is actually also a line that intersects with both points on the torus, right? And we have, for example, this blue intersects with the 2 magenta points. So if n is not a prime number, we might have multiple lines that intersect with 2 points. And here we have already 3 lines, and they dominate twice as many points as they would if 10 would be a prime number. So here we have basic, like really elementary number theory going on, or like trying things out and like finding weird bounds. So what do we get from this? We can, first of all, we can prove a lower bound if n is prime. That is, it's actually an exact lower bound of square root 2n. And the proof of this lower bound is a very simple counting argument. If n is prime, we just said that the two lines intersect at most one point. So if you have 2 points, they really only span one line, and this line dominates n points. So if we have a set of m points, there's at most m choose 2 distinct lines, and each dominates n points. So this thing here is an upper bound of points that are dominated by this set. And if it's a dominating set, then this number has to be, of course, larger than n squared. Now, if you divide by n and you do the math, you find, well, m has to be larger or equal to square root 2n, right? Now, what if n is not prime? If n is not prime and it factors into p times q, where p is a prime factor, q can also be 1, but then this is just a really bad upper bound. The geometric domination number on the discrete torus, the nt, then is bounded from above by 2 times p plus 2. So think about even numbers. We can choose 2 as a prime factor. Then the domination number is bounded from above by 6. Whereas for a prime number, the domination number is bounded from below by square root n. Right? So there's a big difference. And we can actually also show that if n is an even number, multiple of 3, then the domination number is bounded from above by 4. And I actually think this should be inequality, but you know, life is full of deadlines, and I guess that's where we are at this time. Right, so I won't go into all the details of this proof because it's somewhat technical and not particularly interesting, but I'll show you the fun part. Let's maybe consider the 10 times 10 torus again. And well, 10 factors into 2 times 4, obviously. So we can divide this 10 times 10 grid into 5 times 5, 2 times 2 little grids, right? 2 times 2, 2 times 2. And then we take, for example, 2 points on this little 2 times 2 torus, and we blow it up by a factor of 5. So we end up here. And there's a somewhat technical lemma, I would say, that says essentially, like, no matter what the prime number here is, but we get a copy of this line that is spanned by the 2 points on the small torus in each of the small grids, except for the points that are congruent to 0, 0. Here you need to be careful. In this case, 2 and 5 are co-prime. There it's no problem. Here also the points congruent to 0, 0 will be dominated. If these 2 numbers are not co-prime, like if this would be, for example, 4 on the 8 times 8 torus, then this is not true. There would be some points that are congruent to 0 that are not dominated. So there's a bit of a like detailed thing going on, but the point is we get this copy of these this line on the small torus in each of the small tori. And now we already dominated half of the points on the torus. And well, now I leave it as a very easy exercise to find 2 points to dominate the rest of the torus. So this construction works for every even number. Like I said, if these 2 numbers are not co-prime, there's a step in between, but basically that's the idea. And that's also the idea for the general upper bound if you factor p times q for the upper bound 2p plus 2. Now, what if n is prime? Then we would only have this general upper bound 2n plus 2, which is really bad because we already know 2n is a trivial upper bound. But we can actually show that if n is prime, that it's bounded, the domination number is asymptotically bounded from above by square root constant times square root n log n. And we do this with probabilistic techniques. And they were mostly developed for random graphs, I think. So I will give you like a short intro into random graphs. And then I will like briefly outline the proof essentially of this thing. And for that, I come back to this conjecture that I mentioned in the beginning, is really an extension of the ideas that they used for their conjecture, and people, I don't know, they love conjectures. So I thought maybe I spread the word, and maybe someone of you is an expert in probabilistic combinatorics and wants to dig deeper in this problem. Right. So this is in a plane. This is the n times n grid in a plane. And Guy and Kelly, they said that they take a set S of size kn uniformly at random from the n times n grid. And k is at this point, we want to determine k. It should be smaller than 2, otherwise it's like a useless result. But at this point, we do not know what k is. We just choose this point set of size kn. And then we compute the probability that 3 random points are collinear, which is something like constant times log n over n squared. I won't go into this computation. Let's just take it as that. And then they say, well, if the events that 3 points are collinear are independent, so if you've never had a course on probabilistic combinatorics or probability, events that are independent, essentially it says intuitively, well, one thing happens and it has nothing to do with the other thing happening, essentially. So if this is the case, then the probabilities are just multiplied. So the probability that both things happen is just a product of the probabilities. So in this case, S contains no collinear triples would be the probability that 3 points are not collinear to the power of number of collinear number of triples in the set of size kn. And asymptotically, we can write this as e to the minus p times kn choose 3. Or like you can also write it like this with this error term. And now, again, since S was uniformly chosen, you know, if you do not know how uniform distribution works, it's just lucky outcomes divided by possible outcomes. So in this case, it would be like the probability should be like number of point sets of size kn without collinear triples divided by number of point sets of size kn. And so if we multiply this probability with the number of point sets of size kn, this should be the number of point sets of size kn without collinear triples. And then they say, well, if k is larger than pi over square root 3, this converges to 0. So if n is large, this number should be 0, and there's no point set with this property anymore. Now, why is this a conjecture? Basically because of this assumption here. If the events that 3 points are collinear independent, if this wouldn't be an assumption, if this assumption would be true, this would just be a theorem, a proof. But think about like points x1, x2, x3, they're collinear. And then maybe we know that x2, x3, x4 are collinear. But then we immediately know that x1, x3, x4 are also collinear. This event is completely determined by these 2 events. So they're not independent. And so this assumption is basically not true. But well, there have been tools. There's questions in the chat maybe. Okay. So sorry, I lost. Yes, so there has been a couple of tools developed in the last decades, I would say, to cope with dependence of these random events. And like I said, so I used some techniques that are usually used in random graph theory, but they just apply to anything. So maybe I'll give you like a small intro to random graphs, and then we'll go into the proof. So Erdős and Rennie and like others, they introduced basically 2 classic random graph models. Like one is called the uniform random graph, and we denote it by Gn, where n is the number of vertices in a graph, and m is a fixed number of edges. And this number, these edges are chosen uniformly at random from the edge set of the complete graph. So if n is 4, then we have these 4 vertices. And if m is 3, we would, for example, choose these 3 edges uniformly at random, or maybe these 3. And the probability that the random graph would look exactly like this would just be 1 over number of edges in the complete graph, choose m edges. Then there's another random graph model. It's called the binomial random graph, and we denote it by G and P, where n is again the number of vertices, in our case 4. And P is a probability, a success probability. Let's say 1/3, for example. And then we consider each edge independently. So we ask this, we take this edge and then we throw a coin, and with probability P, we take the edge into our graph, and with probability 1 minus P, we just leave it out. And we do this independently for each edge. And what we see, we expect the graph to have n choose 2 times P edges. But we might end up with the complete graph. We might end up with an empty graph. So here the number of edges is fixed. Here it is not. But here we have the advantage that we consider each edge independently. And this is basically the reason why it's easier to consider dependence of events in this model. And if you think about it, what we've really done now is we just chose a random subset of a given set, namely the edge set of the complete graph. So here we chose a random subset uniformly at random, and here we chose a subset where we considered each element of the set independently and threw a coin. So we can also do this for point sets. We just take R and M, where n gives us the size of our grid. So in this case, n is 4. We would just have the 4 times 4 grid. And then m gives us the number of points that we choose uniformly at random. For example, here this would be 3. And then the binomial random set, again, n is the size, 4 times 4. And then with probability p, we take each point, we throw a coin for each point individually. And with probability p, we take it into our set or not. And yes, so the probability that a random point set looks exactly like this set would just be 1 over n squared, which is the number of points in the set, choose m. And the probability that random binomial random set looks exactly like, okay, I didn't finish this set, but looks like a fixed set is just p to the size of r times 1 minus p to the n squared minus size of r.
Okay, just one interruption. There was a question in the chat for the uniform model for the graphs. It seems that we are regarding isomorphic graphs as different. Is this correct?
Yeah. So we yes. So we label the vertices. We label the vertices, and then we have, for example, the edge 1, 2, 2, 3, and whatever. And so this set would be the same, would be a different graph than this set, this thing set, yes. Okay, I hope this answered the question. Okay, so the two models relate to each other. This is, for example, a lemma that relates this to these two models, and basically it says that P is a point set property. Like, for example, that P is a dominating set would be a point set property, and then M and M have to satisfy certain conditions. I won't go into these conditions because we're not using the lemma anyway, so just bring it as an example. But the point is the probability that the uniform random point set satisfies a point set property can be bounded by 3 times square root m, so the size of the uniform random set, times the probability that the binomial random set satisfies the property. And like I said, these models are very easier to handle in regards to the dependence of certain events. So these are nicer to work with. So if you want to show that this probability goes to 0 or is smaller than 1 or something like that, then you can just use this inequality and work with this model, and it's way nicer. And actually, we are in the really nice situation that we have monotone properties. So a point set property is called monotone increasing if adding a point does not destroy the property. So for example, if we have a dominating set and we add an arbitrary point to it, it will still be a dominating set. Conversely, we can also talk about monotone decreasing properties. For example, if we have a point set without collinear triples, removing a point does not destroy the property, no matter which point we remove. So, so this would be a monotone decreasing point set property. And if you have monotone properties, this inequality that I've just shown you is way nicer. We do not have these restrictions on these properties that M and M has to satisfy. The only thing that has to be satisfied is that M is n squared times p. That means we expect the binomial random point set to have exactly m edges. This is the only thing that needs to be satisfied. And then we can bound the probability that the uniform random point set satisfies a property by 2 times the probability that the binomial random point set satisfies the property. Right. So basically, we will just use this model and show that this probability goes to 0. Right. So let's get to this upper bound on the torus. Right. The idea is essentially, well, if S is a dominating set, then for all S that are not in the set S, there exists a dominating pair. So there's 2 points in S that span a line that dominates S, X. And now random point sets of size M. And later we will find out that this M is some constant times square root n log n. And we showed the probability that there exists an X that is not in R and M, sorry, without a dominating pair is strictly smaller than 1. And we will do this essentially just with tools that I've shown you. First, we fix a point X, and we define Px to be the property that this point X is not in the random point set R and M, and there's no dominating pair of X in R and M. And then we compute the probability that the binomial random point set with success probability m over n squared satisfies this probability. And to bound this probability, we use something like an inequality, Janssen's inequality. If you do not know this inequality, I think it's well known in random graph theory or in probabilistic combinatorics. If you do not know it, it's not too important. The point is that this probability is has an exponential bound. It's bounded by e to the minus mu plus delta. And mu is the expected number of dominating pairs in the random point set. And delta reflects the variance. That is, delta is actually an upper bound on the variance of the number of dominating pairs. And so here comes the dependence of events into this game. So if the events are independent, would be independent, then this would just be 0, I guess. And well, then, and if delta would be 0, then we would just have e to the minus mu, which is essentially about the thing that I've shown you before, like this upper bound that Guy and Kelly came up with. So I did the computation for the no 3 inline problem, and here the delta was too large. So here was the dependence too large in the binomial random point set by a factor of log n, so it didn't go anywhere. But here we're in a really nice position. We get for the expectation, we get m squared over 2n as the dominant factor. And for the variance, we get, or the delta term, we get m to the m cubed over 12n squared. And then now we can choose m, like that we have a really nice result. We just say, well, what is the probability that there exists a point x that is not in the set and not dominated by R and M? then here, this inequality, this is basically the union bound. If you do not know it, don't worry, it's a classic. And now we can just plug in this probability that we just computed that was independent of x. So this is just n squared times this probability, and this comes of it. And now if we choose m larger than 2 square root n log n, then this probability converges to 0. So at some point it will be smaller than 1 in particular, and we know that there exists a dominating set of size 2 plus epsilon times square root n log n. Do you have questions to this probabilistic thing? Was it? Yeah. Okay, because that was basically the proof of the upper bound for the domination number on the discrete torus. So maybe I'll do a quick summary what I've shown you. In the Euclidean plane, the domination number is bounded from below by n to the 2/3. It's bounded from above by n if n is even, n plus 1 if n is odd. And well, we have a conjecture for the independent number, for an upper bound on the independent number, but we've seen that it's based on an assumption that is not true, and we do not know how to handle this independence. And then on the discrete torus, for n is prime, the domination number is bounded from below by square root n and from above by square root n log n. And for composite numbers, n that factor into p times q, where p is just a prime factor, we can bound it from above by 2 times p plus 2. Right. So yeah, that was a quick talk. Do you still have any questions, or do you want maybe proofs on these things? I think I have extra slides, but I thought. Yeah.
Maybe let's first thank Eva for the talk, or should we go to the extra slides? No, I think we will. Thank you. So you can either clap virtually or unmute yourself and clap. Are there questions? Mark, are you raising your hand for a question?
I am raising my hand for a question.
Okay, then go ahead.
So the first question I had is, so IN is the smallest dominating set with no collinear triples, right?
Yes.
Are we guaranteed that IN exists in just say the n by n case or in the torus case?
Yes. Basically, you could just start with the point and greedily add points. As long as you do not have collinear triples, you just add points, and at some point you will just run out of possibilities. And then
right. If I ever run out of points to add, then whatever I have has to be a dominating set. Okay. Right.
In both cases, yes.
Yeah.
I have a question. So you have shown us the n times n grid. What can you say about the n times n grid? So can you project results down there, or is it a complete different story?
I don't think it's a complete different story, but I've actually never thought about this, to be honest. So people considered the no-3 line problem on the discrete torus, and they solved some cases of the n times n torus. So this would definitely be a thing that one could look into. Let me just see. I think I have the some. These are my leftover slides. So here, for the n times n torus, if n and q are prime and m is n times q, the problem is solved in this paper of Fowler and collaborators from 2012. Yeah, and then there's also here the maximum number of points without three in a line on the n times n torus is at most 2 times common divisor of n times n. So you can see here's also some elementary number theory going on technically. Yeah.
Thank you. Are there any further questions from the audience?
I had another further question. So because we're talking about extensions, has this problem been considered where you're allowed to pick points that aren't on the grid?
Yes, we've thought about this a bit. It's actually featured on this conference paper where we presented it in June. And we know, for example, that for like a very small grid, I think it's the 2 times 2 thing or something. We only need 3 points if you can place the points outside. So I can show you. Maybe there's. I actually like to work here. So if this is your 2 times your 4 times 4 grid, and you place a point here and here and here, then all the points in the 2 times 2 things are dominated with only 3 points. This wouldn't be possible if you're only allowed to place points within the 2 times 2 grid. But we haven't found any examples for larger grids as far as I know. And it's computationally, it's like really hard because there's no efficient algorithm to find these dominating sets. This is also the problem about the no-3 line problem, which is why it's interesting to computational geometry people, basically, because there's no efficient algorithm to compute these things.
So the example you just gave was picking points outside of the n by n box. What about picking points not on the grid? Because we're allowing lines to kind of not travel along the grid. So can I pick a point in the middle of my box?
Okay. No, we haven't considered this.
Okay.
No. But I guess, I mean, this would probably only be interesting if you're allowed to pick points with that are not rational or something. Maybe because otherwise you could just refine the mesh essentially. Well, then that's not true. You're right.
Okay.
Maybe this is an interesting variant, yes. So yes, no, the study of these point sets actually, it really started 2018 or maybe even later, some time to find someone who's really interested into this minimal version, essentially.
Okay. Yeah.
Hi.
Go ahead.
Yeah. So there's this concept of a visible point where you have this point at the origin, say, and then you put a line to all the points you can see from the origin. And so if you have this, then you say make a line between A and B, and then you can extend that line, and then all of the points lying on that line will be covered. So the visible point is something like P comma Q, where P and Q are coprime, and all the factors are then thus covered. So if you like extend the line, yeah. So this sort of seems like the coordinates of the points could play some role in this scenario. And
the coordinates of the points, excuse me, what?
So the coordinates of the points where they are coprime. So I don't know how this exactly relates, but
so
it seems like a very similar question where we are trying to make lines and then find the constant line.
This is actually part of the proof for the lower bound in the n times n grid in the plane. So basically what you do is you do this counting argument that I showed you on the torus for n is prime. But here, let's say like that. So you count lines and how many points the lines dominate. And this is connected to what you said, like the visible points. So this would be basically the visible point. From if you fix this point, yeah, this is a visible point, this is a visible point, and here again, and they are basically the generators of these lines. And they also give you the number of points that are dominated by these lines. And then you have a more refined counting argument, basically like this S here. Wait, let's go back maybe the proof. Like, yes, this S here, you can compute it. It's I actually forgot the asymptotics for it, but it's connected to these visible points. Essentially, you count the visible points from this point here, and then you do this counting argument again. So, but I couldn't obtain any better results from this idea, but you're absolutely right. Yeah, okay.
I have one further question, because in the beginning you said maybe let's not call it grid, but a lattice. You could also choose another lattice. Do you get some other interesting problems or results there?
I don't think so, to be honest.
So a triangular lattice.
Ah, okay, a triangular lattice. I haven't thought about this, but maybe this would also be a fun thing to do. Yeah, it's a nice idea.
Okay. One more round of question. Does someone else have any question? Okay. If this is not the case, let's thank Eva again for her excellent talk. And we can now stop the recording and maybe have some chit chat or some questions off record if someone wants to ask some more.